last video for Monday, October 26th, and we have homework, which is the IMF FRQs, and there's a video to watch on hybridization because we're going to have an open notes quiz on 2.7, 3.1, and 3.2 tomorrow. We won't go over hybridization, sigma, and pi bonds in class, but the quiz is going to have a couple of questions on that. And then I've assigned the Unit 3 PPCs on AP Classroom, and these will be due Wednesday, 11/4. So this opener, I just asked people to tell me what they thought about why water was a liquid, table salt is a solid, and oxygen is a gas. Got some good feedback there. So Unit 3 is about intermolecular forces and properties. What makes things sticky? So before we talked about intermolecular forces, we did a quick pair deck, and I'm just going to go through the questions and give you the answers that we did for the questions we did in class today. So what type of bonds hold MgCl together? Well, that would be ionic bonds. We have a metal and a nonmetal. So we have an ionic compound. So we have ionic bonds holding together this substance. Okay, next. We now have glucose, which is all nonmetal, C6H12O6. So a molecular substance is held together with covalent bonds. We have covalent bonds inside of the molecules. So those are the bonds in glucose. And then this lead apron made out of a metal would have metallic bonds. Calcium carbonate is ionic, would have ionic bonds, and amino acid has covalent bonds, and sodium hydroxide is ionic. Vesper geometries. So back from Unit 2, we still need stuff from Unit 2 for Unit 3. Chemistry builds on itself. So methane is tetrahedral, 4 electron domains. Ammonia has 4 electron domains, but one of them is a lone pair, so it is trigonal pyramidal. And water, again, 4 electron domains, but 2 are lone pairs, so water is bent. Now, polar and nonpolar, you basically have to drag these red circles and squares, but we'll just put the answers here. Methane is nonpolar. Ammonia, because of its trigonal shape, it's got the lone pair here, but then the nitrogen is attached to 3 hydrogens here. So we have a overall dipole that goes like this. Okay, and we have a partial positive charge on the hydrogens and a partial negative on the nitrogen here. So this is a polar molecule, and most of you probably already know that water is polar, again, due to its shape and the electronegativity of the oxygen. Okay, a couple more examples. If you look at this XC, this is a square planar geometry. So the dipoles all cancel out, okay, because they're in a square, and this is nonpolar. Here in formaldehyde, we have a dipole that goes towards the oxygen, the electronegative oxygen. Formaldehyde is polar. Here we have a lone pair, and this is bent. So we have a oxygen is slightly more electronegative than nitrogen. So something like this, okay, on the NO2 minus the nitrite ion. So this is polar. Here we have an even distribution, and also CH bonds are nonpolar, or considered nonpolar, even though there is a slight difference in electronegativity. The bond is considered nonpolar, so this is only nonpolar bonds, so the molecule is nonpolar. Okay, methanol with the oxygen here is polar. Pentane, all CH bonds, CC bonds, all nonpolar bonds. Pentane is nonpolar. For the same reason, isopentane or 2-methylbutane is nonpolar. All right, so, and by the way, you don't need to name these things. These are organic names, but that's just for your edification. All right, so why are ionic compounds all solid, whereas molecular compounds can be solid, liquid, or gas? Basically, the solidness of ionic compounds comes from the strong ionic bond in a crystal lattice. So we have lots and lots, okay, like Avogadro's number of ionic bonds holding together a crystal. This strong electrostatic force, because we have actual charges here, okay, is causing the ions to stick together and to solidify the compound into a solid. Okay, and the structure of the ionic compound is such that it has the attractions outweigh the any repulsions, right? The ions are ordered so that positives and negatives are next to each other, rather than positives and positives and negatives and negatives. So this solidifies the compound. Whereas with molecular compounds, as we're going to see, right, molecular compounds can be solid, liquid, or gas because the molecules are held together by IMFs, okay? And we're going to talk about what IMFs are in a moment, okay? But these are weak attractive forces that are not chemical bonds, okay? These are weak attractive forces that are not chemical bonds that are holding molecular solids and liquids together. Gas, they're completely separated. But this is the reason why molecular compounds can be all three. It depends on the strength of their IMFs, whereas ionic bonds are going to always cause an ionic compound to be a solid substance at room temperature, that is. Let me put that there, at room temp. Okay, so we did this Pivot Interactives lab, and I had you guys work in breakout rooms to do the activity together. So you discussed the questions and you worked on the activity. The activity looked like this. This activity had 4 parts, and this activity compares the surface tension of various different liquids by putting a drop between these calipers. And they stretch the liquid out, and you measure how far the liquid can stretch before the droplet breaks. Now, when doing this experiment, basically, you need to make a decision about when you're going to measure the droplet and where you measure it when it's stretched out. So make a decision about that after you look at these. After you look at one, you can change the liquid by going to the change button and loading the next video and then watching that. So you can look at different liquids that way. There are questions for you to answer, and then there's text for you to read that refers to the phenomena that you just saw and the different sort of intermolecular forces. For example, here are the temporary dipoles that are set up between non-polar substances. All molecules, in fact, have LDFs, London dispersion forces. So depending on the size of the electron cloud, how squishy it is, how polarizable it is, these dispersion forces can be quite strong. So then afterwards, it'll go on to looking at some more substances. Again, here, you'll have to change to go to a different substance after you watch one. And then it'll ask you to make some predictions about the different molecules. So after doing this, we discussed, these different substances here, and in particular, the fact that this image right here is inaccurate. It labels this as a strong dipole attraction. That's actually not a strong dipole attraction. Here is the dipole attraction here where we have a dipole from the electronegative oxygen. And this is actually a hydrogen bond where we have the hydrogen attached to oxygen attracted to the lone pairs of the oxygen in a different molecule. Over here, this is a dipole from this oxygen inducing this temporary dipole on this CH, this carbon and hydrogen part of the molecule, the more nonpolar part of the molecule. And then this shows a weak, London dispersion force between the nonpolar regions of pentanol. Okay, so there's a lot going on in pentanol. So we can see that pentanol has dipole-dipole forces, has London forces. It also can hydrogen bond. So based on this, you're asked to make a prediction about these, and we talked about exactly, what it is that's causing the different surface tensions in these molecules. And here you do another test of these three substances. In general, surface tension, right, increases as the intermolecular forces increase. So, and then going back to LDFs, up here, right, the longer and straighter your molecule is, the more linear and longer your molecule is, the more contact area it has for forming instantaneous dipoles or temporary dipoles. And so the more contact the molecules can have, the more dipoles are created. And so you have stronger and more London dispersion forces, which hold some molecular substances into solids and liquids, even if they're nonpolar. Okay, remember, LDFs exist in all molecules, but nonpolar things only have LDFs. Polar molecules can have dipole-dipole forces, and special polar molecules, like water, they can do hydrogen bonding if they are special molecules, and we'll talk about that in a little bit. Our slides. So again, here, we want to just label and list our intermolecular forces. So we have London dispersion forces. All molecules have London dispersion forces. However, nonpolar molecules only have London dispersion forces because they have no polarity. 2, dipole-dipole forces. These are for all polar molecules. So all polar molecules have dipole-dipole forces because they have permanent dipoles that can interact. Right? If you have a molecule with a dipole like this, right, it can be attracted to another molecule that has a similar dipole and attract the molecules together. Now, hydrogen bonding is between special polar molecules. This last force, ion dipole forces, this is between ions and polar molecules, particularly in solutions, especially with water and ions. And we'll discuss this more when we get to solutions, as well as dipole-induced dipole forces, interactions, more when we get to solubility. So kind of a side note, I put this in here, but these 1, 2, and 3. These are considered IMFs. So the polarizability of electron clouds. Electron clouds are not as, not hard things. They're actually floppy and they're squishy. the kind of the squishiness depends on the size of the electron clouds. So when you have a squishy or floppy electron cloud, fluctuations and distortions in the clouds can occur, and they can be squished around, and the electrons can be moved from place to place so that you have more electrons in one area than another, and this causes those temporary dipoles to form. Here we have some startling murmurations, which kind of mimic electron clouds and their squishiness. So these temporary dipoles, when they happen, right, can induce temporary dipoles in other molecules next to them. So even if you're nonpolar, you can have a distortion in your electron cloud and create temporary dipoles which can attract each other. So all molecules have these forces again. And the easier you can distort the electron cloud, the easier and squishier and more floppy this electron cloud is. That's called polarizability. And the polarizability is directly related to the strength of your LDFs. So the larger your molecule is, the larger your electron cloud of your molecule is, the more polarizable your molecule is going to be. And when you're more polarizable, you have stronger LDFs. The longer, straighter chain of atoms you have in your molecule, the more surface area or contact area is there for LDFs to attract each other. Okay, so this will create stronger LDFs again. So here we can see this trend with group 14. Let me put that as 14. And this IPF terminology, my friend likes to use IPFs, but IMFs is kind of what the AP exam uses, so I'll use IMFs. So here you can see that as we go up the group, the molecules are getting smaller. Or as we go down, the molecules are getting larger. Their electron clouds are getting larger. They're becoming more polarizable as we go down the group because their electron clouds are floppier and squishier, less tightly held. So as we go down the group, boiling point increases because things are getting more polarizable, stronger LDFs, harder to boil the molecule, right? In order to boil, we're taking these particles here, like if we have CH4, we have to unstick them from each other, right? We got to separate these and turn them into gas. We have to completely break the intermolecular forces. So here we can see this trend as we go down the group. So in terms of these two noble gases, right, we'd expect krypton to have the higher boiling temperature because it has a squishier, a larger electron cloud. Larger electron cloud. If we take a look at the periodic table, krypton is in group 4 and neon is in group 2. So many more electrons, more shells. It's going to be more polarizable, more squishy, which means that it has a higher boiling point, boiling temperature. Here we have halogens, and I'll give you the states of matter here. Fluorine is a gas at room temperature. Cl2 is a gas, and let me qualify this at room temperature, at a specific temperature here. And bromine is a liquid, and iodine is a solid. So the halogen with the highest boiling temperature has to be iodine. It is a solid. Oh, I just wrote iodine here. That's not what I meant to write. Solid. Okay. Iodine is a solid, so it has the strongest LDFs. These are all nonpolar. Strongest IMFs, okay, strongest LDFs, because it only has LDFs. So this is going to have the highest BP. It's always good to identify the IMFs in each of these substances and write them down in the beginning so that you can compare and figure out what is causing the difference in the boiling point or some other property that they ask about. Okay, so here again, we're talking about you can see that iodine's boiling point is much, much higher than fluorine's because it's so much more polarizable and it has a much larger electron cloud, so its LDFs are much stronger. The next type of intermolecular force is called a dipole-dipole force. This is when we have a permanent dipole in a polar molecule and there's attraction between the positive and negative ends of the molecules. So these will attract each other and they will stick together due to Coulomb's law. So looking at here, if we look at the Lewis structures for these two compounds, we have CO2. So first thing you should do in this question is draw out the Lewis structure. This is nonpolar. Okay, SO2 is going to be, let's see, 18 electrons. So we have something like this. Okay, and there are a couple resonance structures here as well, but this is bent, whereas CO2 is linear. So a bent molecule with differences in electronegativity is going to be polar. So then once we figure this out, we want to label and list our IMFs. So in SO2, we have LDFs and dipole-dipole forces. Here, CO2, we only have LDFs. So CO2 will boil at the lower temperature because it only has the weak LDFs to hold the CO2 molecules together, whereas SO2 also has dipole-dipole forces from its permanent dipole, which can attract and cause it to stick together more tightly, and so it's harder to boil the SO2. All right, so hydrogen bonding is kind of the ultimate dipole-dipole force. Basically, hydrogen just wants to have fun. And hydrogen, okay, when it's attached to Fon, okay, that's F, O, or N, fluorine, oxygen, or nitrogen. They're these very highly electronegative atoms pull electron density away from the hydrogen, making these quite electropositive, partially positive, and partially negative for these electronegative atoms. And so we have the lone pairs of the electronegative atom attracting the hydrogen that's attached to the F, O, or N in a different molecule. Okay, so remember, intermolecular forces mean forces between molecules, okay, between the molecules. We can also have hydrogen bonds between different molecules, different substances. So here, right, if water can hydrogen bond here, and it has a partial positive charge on this hydrogen, it can be attracted to the lone pair of ammonia here, which is partially negative. Just remember, hydrogen bonds are something that a molecule does rather than something a molecule has, and hydrogen just wants to have fun. Those are two good quotes from friends of mine that that I've stolen and shared with my students because they're good ways to remember things about hydrogen bonding. So here we can see that these group 16, okay, group 16 elements, the hydrides, follow the same pattern of increasing their boiling point as we go down the group or decreasing as we go up the group. Okay, just because of the polarizability of the electron cloud changing as the molecules get change in size. Now, the weird thing is that when we get to water, there's a huge spike in the boiling point. And that's because of hydrogen bonding. That hydrogen bond, those hydrogen bonds between the water molecules is a very strong, very strong intermolecular force compared to the dipole-dipole forces and LDFs in these three molecules. So that's what causes this unusual behavior. The same thing happens with the group 15 elements. They're not shown here, but we see the same trends where we see a spike, and that's too high, but we see a spike in ammonia. So NH3 is very high compared to things like PH3, AS, H3, and so forth. So we see a similar pattern for the group 15 hydrides. All right, so we've been talking about intermolecular forces. However, not all substances are molecular, so we have to be careful here, right? If we have two molecular things, yes, we can talk about their intermolecular forces. But if we have other substances mixed in with molecular substances, we have to know what forces are holding those particular types of substances together, and we're going to talk about this in terms of solids, solids at room temperature. So molecular substances, right, can be liquid, solid, or gas, or solid, liquid, or gas, right? Molecular can be solid, liquid, or gas, but the rest of the solids are going to be different types that are solid at room temperature and are held together with different types of bonding. So we always want to figure out the substance by type first, before we go on to talk about intermolecular forces or the bonds that hold together these substances. So here we've talked about molecular solids. These are nonmetals, that come together to make molecules, and the molecules are held together with IMFs. They're much weaker than true chemical bonds. Here's a covalent bond between hydrogen and oxygen. It's like 400 kilojoules. These weaker IMFs right here, these are the IMFs, are much weaker, but you see that there's a range, right? Because it'll depend on the molecular substance and its polarity or its non-polarity or the length of the chain, exactly how strong these different forces are. Then we also have ionic solids, metals and nonmetals together, and the things that hold ionic solids together are Coulomb's law, the electrostatic attraction. We have real charges here that are strongly attracted, and we can talk about lattice energy, right? So it will show us a little bit about how strongly these ions are attracted to each other. And those two factors in Coulomb's law, again, are the charge of the ions and the size of the ions, which influences distance between the ions. So Don't forget Coulomb's law. Coulomb's law is the basis for all bonding. Okay, and so we're going to always think about Coulomb's law when we talk about attractions. All right, network covalent solids is the third type. Now, these are actually molecular solids, but they have very, very high melting points compared to some. And they are held together with a network of bonds. And these basically, yeah, there's no other way around this. You just have to memorize these network covalent solids. There are definitely other network covalent solids besides these, but these are the ones that the AP exam focuses on. And we have two substances, diamond and graphite. That's on the next slide, where their melting points are just huge. Okay, it's very, very high compared to ionic solids or most metals. And this is because they are covalently bonded to each other, and they're a giant molecule. Basically, a diamond is a single giant molecule. They're very hard and strong substances. Now, graphite is strong, but it's these sheets, and there are LDFs that hold together the sheets. So it seems like it's very slippery and easy to take apart, but that's because all you're doing is breaking these LDFs when you use a pencil on paper. A pencil has graphite in it. So, but these sheets are held together and have a very high melting point, and they're actually able to conduct electricity because I didn't talk about this in class, but each of these there's a pi system, a system of pi bonds of double bond electrons, which can actually be shared across the whole sheet. And so graphite actually conducts electricity and has a very high melting point. Two more covalent network solids. Here's quartz and here's glass. Okay, they are the same compound, except that quartz is crystalline. It's a very very ordered structure, whereas glass is amorphous. It doesn't have a clear crystal pattern. All right, and then finally, metals and alloys we've already talked about before. And here's our metallic solid with our positive metal ions with a sea of electrons surrounding it. And so those are our metallic bonds and our metallic substances. Alloys have the same properties as metals, just changed properties depending on the alloy. All right, so what we want to ask is, right, is the substance ionic? Then we're going to just use Coulomb's law and lattice energy, okay, to figure out which one is going to have a higher melting point. Okay, so those, we'll just look at those. Is the substance a network covalent, right? Is it one of those? And if it is, then remember, these are going to have very high melting points. Sorry, that does not look like MP at all. High melting points, right? Because we got to break all of those covalent bonds apart in order to melt this. So if the substance is molecular, okay, then we're going to look at the molecule size, the size of the electron cloud. We have to look at whether it's polar or nonpolar. We have to look at hydrogen bonding, right? Those are all going to affect our IMFs. Okay, but basically, if we have a mixture of these things, right, we're going to have to think about what bonds are being broken when we melt a solid of this type. So, right, if we have an ionic compound, we have to break ionic bonds. If we are melting, let me put melting here, right, to melt a ionic compound, we have to break ionic bonds, right? For here to melt We have to break covalent bonds for a network covalent solid. For a molecular substance, all we have to do is break IMFs to melt. Okay, so just remember the distinction between these types, and that will help you determine whether what exactly is being broken when you melt these things or boil them. So what properties are affected by intermolecular forces? Well, here's a whole list of them. Believe it or not, all of these are affected by intermolecular forces, every single one. And we will look at more of these in more details. 8 when we get to thermochemistry. Okay, again here, number 9 in thermochemistry, we'll talk about that more. Surface tension, we've already looked at. Viscosity is how easily a substance flows, specifically a liquid substance. Okay, though we can actually we can have gases flow too, so that I should keep those in there. State of matter at room temperature is affected by intermolecular forces. Melting point, how easily something melts. Solubility, we will talk more about that later in this unit. Okay, this is how a substance dissolves, how much a substance dissolves. Okay, vapor pressure, I will show you a picture of this tomorrow, but vapor pressure is the gas pressure from a liquid in a sealed container. And then boiling point, how easily we can change things from liquid to gas. Okay, and melting again is from solid to liquid. Okay, heat of vaporization is, this is liquid to gas. And heat of fusion is when we go from solid to liquid. The energy required for those phase changes. And we will talk more about those things when we get to thermochemistry. So again here, let me correct this to IMFs, just because IPFs, while more accurate, is confusing because we don't use that terminology. Okay, so we can look at these different properties and decide, are we going to have high or low IMFs? Does high boiling point go with high or low IMFs? Does high vapor pressure, how much vapor a liquid produces when sealed, is that going to be high or low IMFs? So we can look at all of these different things, and we will start off with this list of properties and figure out, do we have high or low IMFs if we have high values for these properties. Okay, so IMFs are really important in our physical world because they kind of dictate properties of matter, and they're directly related to the structure and polarity of substances. So just remember, always classify your substances, know what type of substances you have, whether they be ionic, covalent network solid, molecular, or metallic, and then identify the forces in the substances that are holding it together into a solid or liquid, and then based on that, answer your question. All right, let me know if you have any questions on IMFs.